Okay, on to our practice problems. So, a 105-gram hockey puck is sliding across the ice. A player exerts a constant 4.5 Newton force over a distance of 0.15 meters. How much work does the player do on the puck? We have two equations. For work, we know work is equal to a force being applied over some distance or displacement, or work is equal to a change in energy. Now, we know a force and a displacement, so that top one might be the most convenient equation to use. So that would be the force multiplied by that displacement. Okay. 4.5 times by 0.15, 0.675, and this is work, so it's going to be in joules. What is the change in the puck's energy? Well, this is convenient because we just solved for the work, right? We know the work is 6.75 joules, and we know work is equal to change in energy. So what is the change in energy of the puck? It has a change of energy of 0.675 joules. Okay. Example number 2. Same hockey puck from example number 1. If the hockey player exerts twice as much force now on the puck, how would the puck's change in kinetic energy be? So let's think through this. The puck is sliding across the ice. It's not raising off the ice or sinking into the ice. So potential energy is not changing. It's kinetic energy that's changing. So we just need to recognize that change in energy, which is the work. And so work is force times by that distance. The work is doubled now, so it's 9 newtons. The distance is the same. And so it would make sense that if that force doubles, then the work would double. Okay. And work is the change in energy. In this case, that's the change in kinetic energy. And so that's 1.35 joules. If the player exerts 9 newtons of force, but the stick was in contact with the puck for only half the distance. So we double the force, but we reduce the distance by half. So work, force multiplied by distance, our force is 9 newtons, and the distance is half as much as what it used to be. We get what we originally started with. Okay, and that would be work is change in energy, and in this situation that would be change in kinetic energy, so it'd be 0.675 joules. Nice. Example number 3. When a club strikes a 46-gram golf ball, the ball gains 43 joules of kinetic energy. A constant force of 2,300 newtons is applied to the ball while the club head and ball are in contact. Over what distance is the club head in contact with the ball? Okay, it doesn't talk about height or anything, so let's make this assumption. It's kind of like the hockey puck, that the golf ball is hit, but it travels all linearly, okay? So it doesn't go up or down. So that change in energy would be all kinetic again. So work is force multiplied by the displacement in which the force was being applied. So over what distance is the club head in contact with the ball? That would be that displacement there. So work divided by force. We also know that work is a change in energy, which in this case is a change in kinetic energy. So that would be kinetic energy final, which is 1/2 mass velocity final squared, minus initial. Initially, though, the golf ball was stationary. The velocity was 0. So that would make this whole thing 0, right? And we know that the ball gains 43 joules of kinetic energy. So that must mean that the final is the 43 joules. So work in this situation would be 43 joules. So that would go there. We know the force. Okay, so I'm going to take my 43 joules divided by 2300 newtons, and I'm getting a distance of 0.01, so 2 sig figs. Leading zeros are never significant, so 0.019 meters. Okay. We could do a quick unit analysis to make sure we do end with meters. We're taking work, which is in joules. That's a kilogram meter squared per second squared. And we're dividing it by a force, which would be newtons, so that's a kilogram meter per second squared. Anytime we divide by a fraction, that's the same as multiplying by the reciprocal. Then a whole bunch of stuff cancels. Accidentally, that's not squared, right? It wasn't squared. And so, so we're left with meters. Okay, so we ended with what we thought. For our examples here, this is a very, very simple way of just kind of looking and recognizing, is the force causing work, a change in energy on an object, and the force has to be parallel to the direction of motion. So when the force is parallel, or I should say when the sum of the forces is parallel to the direction of motion, then work is being done. Okay. On to learning target number 2. So last time we talked about work for learning target number 1. Now we're going to talk about power for learning target number 2. Okay. Our equation for power is work over time. How much work, how much change in energy is happening over a given amount of time. Units. Work is joules, which is a kilogram meter squared per second squared, and I'm dividing this by time, which will be in seconds. Okay. Divide by a fraction. It's the same as multiplying by the reciprocal. So we get this really interesting kilogram meter squared per second cubed, and that is a watt. Okay, call that a watt. We have another equation for power, and that is force multiplied by a velocity. So let's see if we end up with the same units here. So force is a newton, so that'd be a kilogram meter per second squared, and we're multiplying that by velocity, which is meters per second. So we end up with a kilogram meter squared per second cubed, which is a watt. Okay, so we have 2 equations for power. Now, one of the more common units of power is horsepower. And so our conversion factor here is that 1 horsepower is the same as 0.75 of a kilowatt. Kilo meaning 1,000. So there are 1,000 watts in 1 kilowatt. Okay? And we want to know, if we have 797 horsepower, how many kilowatts of power would that be? Well, I'm starting with 797 horsepower, okay? Using my goalpost method here. I'm going to put horsepower down below so that it cancels, okay? And in the upper right-hand corner, this is where you put the units that you want to end with. And once you recognize these units, you can find the conversion factor. And up here, it tells us that 1 horsepower is the same as 0.75 kilowatts. So this multiplied by this divided by that 597.75 kilowatts, or 597,000 watts. I want you to just take a moment, you could even hit pause, and look through how many watts are used for these common household appliances, just so you can start making comparisons here and start to get an idea, a well-rounded idea of what we mean by a watt and how that compares. Okay, where are we at time-wise? All right. So, energy and power, what's the difference? Well, energy is interesting. Energy involves changing something for an object, whether that be its height or its velocity or another component. And so a change in that energy is work. Work represents the energy transferred from one thing to another, which results in a change in energy of that object. Power is how fast did that transfer occur. That change in energy happened over what amount of time. Okay? So there's a difference there between work and power. So we have an interesting illustration here. To the right, there's 4 floors. We have 2 TVs identical in mass. And both situations, one we're using a pulley to raise the TV to the 4th floor. The other one we're walking it all the way up the stairs. Okay? Who has done more work? Work is a change in energy. And this time, that would be a change in potential energy, right? Because we're increasing in height. So the mass of the TV is the same. Sorry, let me write this out. So work is going to be a change in potential energy for this situation. And so that would be mgh final minus mgh initial. We'll say that the ground is 0. So that would all be 0. And the mass is the same for both. Acceleration due to gravity is the same. And the height at which they're changing, the height of the TV in the end, is the same for both. So that must mean the change in potential energy is the same, which means the work is the same. They're doing the exact same amount of work. The woman using the pulley gets the TV to the 4th floor in 2 minutes. The man going up the stairs takes 10 minutes. Who generated more power? Power is equal to work over time. So if we have a small amount of time, we have a larger amount of power. If we have a larger amount of time in which that energy transfer would occur, we have less power. Power and time are inversely proportional. When one gets big, the other one gets small. So if the woman spends a smaller amount of time, then her power must be greater than. Okay. So we have examples number 6 and number 7. So I want you to give this a go and then come back for the last video of the day and we'll go through those problems together.